Hello, folks. Hope you're doing well. Today, we'll be looking at deriving the relationships among different soil parameters that we learned in the last video. We'll use the knowledge of phase diagrams and the previous definitions that we already know to derive these relationships. In most cases, we'll assume the volume of soil to be 1 for easy calculations. And specifically, we'll be aiming to derive the relationship between void ratio, water content, saturation, specific gravity of solids, and unit weight, and see how they are related to each other. So without any further delay, let's get started. So the first important relation which we'll be looking at is the relation between weight of water, the total weight, and the water content. So we know that the total weight of water is the sum of the weight of water and the weight of solids. So this can be written as, if we take the weight of solids out common, we will have 1 plus weight of water over weight of solids. And we know that the weight of water, this ratio, weight of water over the weight of solids, this is called water content. So W becomes equals to WS times 1 plus water content. So the relation is WS equals to W over 1 plus water content. This is an important relationship. The second important relationship which we'll be looking at is the relationship between the void ratio E and porosity N. Both quantities are used to describe the relationship between the void space and the solid space or total volume. So let's see how we can derive a relationship here. So we know that the void ratio E equals to VV over VS, volume of voids over volume of solids, and porosity N is equal to the volume of voids over total volume. Now, if we simplify this, we can write N equals to VV, and the total volume can be written as volume of voids plus volume of solids. Now we divide the numerator and the denominator both by the volume of solids. So we have VV over VS, and then we have VV over VS plus VS over VS. Now VV over VS, we know that this thing is equals to E. So this thing is also equals to E, and this thing is equal to 1. So this becomes E over E plus 1. So N equals to E over 1 plus E, which is an important relation to remember. And similarly, if we solve for E in this equation, we can get E equals to N over 1 minus N. Another important relationship which we should memorize. The relation between E and N can also be derived using a phase diagram, as we said that this is an alternative method to derive these relationships. So let's look at one phase diagram, and we have air, water, and solids here. And for the sake of simplicity, let's assume this volume of solids is equals to 1. Now we are left with the volume of voids. According to the definition of void ratio, E equals to VV over VS, and since we have assumed this equals to 1, so this means that E equals to VV. So we can write VV equals to E over here using this relationship. Now, what's the total volume of soil? Total volume of soil should be equal to the volume of voids plus the volume of solids, which in this case, the volume of voids is E, and the the volume of solids is 1. So E plus 1. Now, the definition of porosity N is VV over the total volume, which can be written as VV over this total volume is the sum of voids and solids. So we know VV is E, and this is also E, and volume of solids is 1. So N equals to E over 1 plus E, derived using phase diagrams. Next, we derive the other relationship between N and E. So we again draw the phase diagram. So we have the air, water, and solids again. And this time, for the sake of simplicity, let's assume the total volume equals to 1. Now, according to the definition of porosity, N equals to volume of voids over the total volume. So this is the volume of voids and this is the volume of solids. So if N equals to VV over V and the total volume is 1, so this is VV over 1 equals to VV. So we have the volume of voids is equal to the porosity N. Now, uh, the volume of solids is equals to the total volume of the soil subtracting the volume of voids. So this is assumed to be 1 and this is assumed to be n here. So the volume of solids is 1 minus n. So now what's the void ratio? The void ratio is VV over VS by definition. VV here is n and Vs is 1 minus n from the formulas that we have. So finally what we get is E equals to n over 1 minus n, which we should try to remember. The next and perhaps the most important relationship that we'll be using all our times in soil mechanics is the relationship between void ratio, water content, specific gravity, and saturation. The relationship between E, W, G, and S. So let's look at this relationship in detail. So there is a theoretical derivation as well as a phase diagram relationship, phase diagram derivation for the derivation of E, W, G, and S. So I found the phase diagram relationship easier, so I guess that's what will be more beneficial to derive this relationship over here. So let's look at the phase diagram first. So looking at the phase diagram that we have on the screen, we have the volume side and the weight side of the soil. We have air, we have water, and the solids. We'll be deriving the relationship between E, W, G, and S using the formula that we already know. So as we are already familiar with the formulas of E, W, G, and S, we'll try to use these, and the only thing that we have to do is to connect them with each other and find a relationship that has all the quantities mentioned in the form of an equation. And for that, the assumption that we are using in this whole derivation is that the volume of solids is assumed to be 1. This really simplifies the derivations when we assume the volume of something equals to 1. We could also assume the total volume V equals to 1 or any other thing. We could also assume weight of solids equal to 1 or the weight of water equals to 1. But it's really up to choice, and whatever we choose, we just have to go ahead with that and just find the relationship between other quantities using this derivation. So after we assume Vs equals to 1, so the first thing which involves Vs is E. So if Vs equals to 1, then E becomes equals to Vv. So now if we look at the volume side of our derivation, we know that this is the volume of voids and this is the volume of solids. Now the volume of solids we have already assumed that is equal to 1, and now we also know that the volume of voids is equal to the void ratio upon this, so we have Vv equals to E. The next thing that we look at is saturation, because saturation is also involving volume. Sorry, this is volume of voids in the denominator. So we know saturation is volume of voids over volume of water over volume of voids. Now we know that this is equals to volume of water over volume of voids, which is E. So volume of water can be written from here as E times S. Now we have figured out the volume side of the phase diagram. Now we need to figure out what the weight side of the phase diagram looks like. And to convert volume into weight, we need to make use of something like density or unit weight, so that we could multiply the volume with density to get the weight. Now we know that the unit weight of water is gamma W and the unit weight of solids is gamma S. The specific gravity of water is taken to be 1 and that of solids is taken to be G. These are the quantities that we'll be using to convert the volume side of the phase diagram into the weight side of the phase diagram. So now let's try to calculate the weight of the water first. So weight of water, what should be the weight of water equal to? It should be the volume times the unit weight. So it should be VW times gamma W. So this becomes ES gamma W. Nice. So now let's fill in this over here. So this is ES gamma W. And now also let's try to calculate the weight of solids. So the weight of solids should be equal to the volume of solids times the unit weight of solids. So we know that the volume of solids is equals to 1 in this case for simplification, and this can be written as the unit weight is equals to the specific gravity times the unit weight of water. So this is G times gamma W. So we can fill this here, G times gamma W. Weight of air is neglected to be 0. So this is done. So now we have all the quantities of the phase diagram. Now we just need to connect this. So in order to connect this, the final thing that we have not used in this relation is this. We already used G. So we know the water content is equal to the weight of water over the weight of solids. So now dividing these two, we have ES gamma W over the G gamma W. Now this gamma W cancels out and we are left with ES over G. So now rearranging these terms, we get W times G equal to ES, or ES equals to GW, which is a very, very, very important relationship which we'll be using all the way in soil behavior and soil mechanics. This relation can also be used to derive other important relationships between the soil parameters. Now let's look at another very important relationship between the soil parameters, which is called the relationship between unit weight and the specific gravity, the void ratio, water content, and the unit weight of water. So we will derive a relationship between the total unit weight, and this will be expressed in terms of G, E, W, and gamma W. Very important relationship which we are considering. So if you remember, the total unit weight of soil is the is defined as the weight over volume. This is the total weight and this is the total volume. So what is the total weight of soil? It is the sum of weight of solids and water, and in the denominator we will have volume of solids and volume of voids. These volume of voids, we know this is volume of air plus volume of water. Okay, so if we take weight of solids common from the numerator, we will get 1 plus water over solids, and similarly if we take volume common from the denominator, we will get 1 plus VV over VS. We should be able to recognize most of the quantities that are listed over here. So this thing over here, this is, we know this is the water content, and this thing over here, this is what? This is the void ratio. And what is this thing over here? This thing is the density or the unit weight of solids, which is also written as G times gamma W. So if we put all this in the expression, in the numerator we have G times gamma W, and in the brackets we have 1 plus W, and in the denominator we have 1 plus E. Now if we multiply this G inside of this brackets, what we get is gamma W is outside, this is G plus GW, and in the bottom we have 1 plus E. Now from the previous relationship we know that ES is equal to GW, so put that back into this expression. We'll substitute this, so what we will get is gamma W G plus ES over 1 plus E. So what we need to memorize is any type of unit weight can be represented in terms of unit weight of water times G plus SE over 1 plus E. Now we can have various types of unit weight and we can derive all of them from this one relation. Note that this is the expression of total unit weight that we have derived here. Now suppose, let's say we have different cases, and the first case what we have is of that of a saturated soil. So let's consider a soil which is saturated. So what does saturated means? Saturated means that the unit weight of soil is this time gamma S, and S equals to 1 since it's completely saturated. So what will this expression become? This will become gamma saturated is equal to gamma W G plus SE. Now S is 1, so G plus E over 1 plus E. Very important again. Another important relationship which we have from this is the expression for dry unit weight. Now what does dry mean? Dry means that the gamma equals to gamma dry and saturation equals to 0. Note that in the previous case the saturation was 1, which is now equals to 0. Now we just have to substitute S equals to 0 in this expression. So gamma dry is equals to gamma W times G plus 0 over 1 plus E, right? So this is G gamma W over 1 plus E. So gamma dry is G gamma W over 1 plus E. Another very important relation. The next one which we'll be looking at is the buoyant unit weight. This buoyant unit weight is also called as effective unit weight, or this is represented by gamma buoyant or gamma dash. So this gamma dash is nothing but the gamma sat minus the unit weight of water. So we don't have to do anything, we just have to use the gamma sat that we already calculated and subtract the unit weight of water from that. So what we have here is gamma prime is, we'll use the expression gamma W G plus E over 1 plus E minus gamma W. Now we'll take gamma W common and try to simplify this expression. So gamma W is common, and inside we'll have G plus E over 1 plus E minus 1, and if we do this calculation over here, we will have G plus E minus 1 plus E over 1 plus E, this whole thing multiplied by gamma water, which will be equals to gamma water. Now this E and E will go off, this will be left with G minus 1 over 1 plus E. Expression for gamma dash. Very important relation again. So these three expressions, one for gamma saturated, one for gamma dry, and one for gamma buoyant, all of these can be derived from this master relation, which is very important. So if we remember this one, we can derive any type of unit weight, be it saturated, dry, or buoyant. So I would stress to just learn this expression and then use either S, replace it with whatever we have, and then you can calculate whatever the unit weight you have to calculate. So by remembering this one relation, we can derive everything else. Now let's try to summarize all the important relationships we learned in this lesson. So the first one that we learned is N equals E over 1 plus E. Second one, ES equals GW. Finally, unit weight equals gamma W G plus SE over 1 plus E. These are very important relations and are very, very helpful in solving numerical problems in soil mechanics.